and welcome. So the aim of this video is to create an understanding of covariance and correlation of two random variables. In particular, we're going to be looking at discrete random variables, two of which instantiate together. So a lot of the time in your math stats course, you're going to be looking at continuous random variables, and it's my belief that unless you understand the theory for discrete random variables, there's too much going on, there's too much to think about in the continuous case, unless you're just a total math whiz. So that's why we're going to start with this simpler case. And we want to understand these things, like intuitively, what the symbols mean, how to visualize the joint distribution of two discrete random variables, how to go through the computations to get at these numerical values, and how to use R to simulate the probability scenario that we're going to be talking about. Okay, so that's what we're going to be doing. So the problem, as I see it, is that, okay, looking at covariance and correlation as they pertain to, like, samples is fairly straightforward. In a past video, I at least endeavor to try to show that if you're looking at sample correlation for two variables that for which each individual gets like two measurements, the stock example being height and weight. So you've got 10 people and you've recorded each of their height and weights. This idea of the correlation being something to do with an angle between these, in this case, 10-dimensional vectors, of which you have two. So, I mean, I say it's straightforward. It's actually not so easy, but it's doable. Even if you understand that, though, applying the concept to random variables can be a little bit sticky, just because it's easy to lose sight of what exactly the objects are that you're talking about. So anyway, I say recall all of this, and you don't really need, usually we save recall for if I'm immediately going to use the thing, which I'm not in this case. But I just want to point out this little math stat table that I like to create, because it shows that these larger concepts of taking the mean, variance, standard deviation, covariance, and correlation, they have many different places to which they can be applied. In the case of a sample, a full population, or to probability generating random variables, or data generating random variables, I should say. So the things I just want to call our attention to are, can we actually see my little dots here? Okay, so if you've got samples, a sample of data where you're taking two measurements, like the height weight example, if you've got this kind of increasing pattern, you increase in one, you increase in the other, you've got positive covariance. If you've got sort of scatter about a level line that's parallel to one of the axes, with no clear direction, that would be something close to a zero covariance, and likewise for if as one variable increases, the other one's on the decrease, on the decline. Okay? So I just wanted to point that out. And then this, which I already said or alluded to before, that this correlation coefficient can be thought of as the cosine of the angle between your n-dimensional centered data vectors, and why they need to be centered. I try to broach these things in another video. But the big point is that we just want to note that, like, the symbolism, like how we represent these different concepts with respect to these different areas is different, right? So if you're talking about sample correlation, you get this little R. If you're talking about population, you get a row x, y, and if you're talking about random variables themselves, you can have this operator, but it can also be symbolized using row x, y, which can be a bit confusing, but the whole point is that in random variables we use these operators or the symbols to describe them. Okay. Bear with me for a second. Okay. Okay, so what's going on here? For two random variables, x and y, you can write the covariance of x and y is equal to the expected value of brackets x minus mu times y minus mu y. Sorry, x minus mu x times y minus mu y. And the correlation uses the covariance in its calculation, or in its formula. You're dividing that covariance by the standard deviations of the random variables. Okay, so as I said, the key to making sense of these formulas is to get a sort of easy example of how this could even happen. Like what could I possibly, or what could one possibly be talking about? What does this situation represent? So, I mean, it's easy if you can visualize some actual objects in the real world. So what I've done is I've said, like, suppose you have like 10 slips of paper, and each one is going to have 2 numbers written on it. Now, the first number corresponds to our x random variable, and the second number is going to correspond to our y random variable. So the idea is that if you put these slips of paper into a jar or a box, randomize it somehow, shake it, shuffle it around, and you pick one, what you have in your hand is an instantiation of both random variables occurring together. Okay, so you do this experiment, and you've just instantiated your first jointly distributed discrete random variables. Okay. Now I'll just note here, sometimes, let's see, do I have thing here? Okay. So a lot of the time in math stats, you'll see this situation described by what's called like a random vector. So you might say that you have a random vector z, and you just symbolize it as saying something like x and y are your components of the random vector z. Okay, so I just figured I'd throw that out there because random vectors become important later on. And when you're dealing with more than 2 random variables, you get into like the covariance matrix, and it just gets more complicated from here. But unless you can see that this is the simple case of a random vector, you'd be, sort of at a loss there. So anyway, so I've made this claim that when you draw from this bag, you're getting an instantiation of these jointly distributed discrete random variables. So, can we actually talk about what that joint distribution is? Can we isolate the marginal distributions of the 2 constituent random variables? And is it possible to visualize this? So all I've done here is I've said these are our possible x values, these are our possible y values. I mean, you can have a 1, you can have a 2 or a 3 for x, you can have a 0, a 1, a 2, or a 3 for y. But these things aren't all created equal. Some of them, for instance, 1 and 0, you've got twice the likelihood of drawing that as, say, 3, 3, so only one of these out of the 10. Anyhow, so I just make like a nice little table of the probabilities associated with drawing each one of these slips. 2 tenths, 2 tenths, 1 tenth, blah, 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 blah. You can see that, for instance, okay, what's the probability of drawing a slip that has 3, 2 on it? Well, we've got 3, 0, and 3. Oh, there is no 3, 2, so that's why I've assigned it 0 probability. Okay? And from this, by simply doing totaling down the columns or totaling across the rows, we can look at x and y individually. These are outcomes for x and the probabilities associated, and the same goes for y. Okay, so nice. We've got something that kind of looks like, what might be thrown at you in like a test or assignment or whatever, but now we've got like a real like intuitive idea of like what the experiment is that results in these joint and marginal probabilities. So, is it possible to visualize this distribution in R? And the answer is yes. You would just have to know how. And I'm going to show you how right now. Okay. So what I've done is I've created a vector of x values and y values. And you'll see that these correspond if you look back at the other table. Like 1, 0 was a possible draw, 1, 1 was a possible draw, 1, 2. Okay, so I've taken the possible combinations and the probabilities that are associated with each. Now, I've left out the ones with 0 probability. So, I mean, take that for. I mean, I could have included them. Like I could have had the impossible draws, like 3, 2, and just given it a 0 probability. But I figured, what's the point? Okay, so there's a cool R package called scatterplot3D, which allows you to visualize these things. So if you don't know how to get that, I may as well show it. You'd go Packages, Package Installer, you put in scatterplot3D get list, and you would install it. I've already installed it, so I don't have to do that. Okay, and then once you install it, you want to activate it. Okay, so you just use library, and that brings it to R's attention. The reason you have to do that is because if you have many, many packages, you don't necessarily want R to be having to know what all of them are at the same time, so you bring it specifically into R's consciousness, if you will. Okay, so what I want to do is create a plot of this distribution. When I say type H, that just means I want... Okay, maybe I should explain a little bit more. So this is going to be like a three-dimensional plot, scatterplot3D, where on one axis we have x, on the other flat axis, pretend that this is like a tabletop. You have x and y on your flat axes, and then z is coming up off of the table. So basically we'll get our sample points, or the points in our sample space for these dual instantiations, and then the probability associated with each one. Okay? So this is the code for that. And I can talk you through it a little bit. I mean, we've loaded in our x and y values, and then the probability. So that's the basic format of this 3D scatter plot, is you just put your x, y, and z vectors. Now, I set the z limit to 0.3, and the reason I've done that is because the greatest probability that we have here is 1/5 or 2/10 or 0.2. So I want to be able to see a little bit of clearance above that, some headroom, if you will. But I don't want much more than that. The x and y limits will just be set by the bounds of these vectors, which I'm fine with. Okay. I want it to be colorful, and basically as long as the color in here matches the number of x values you have, you're fine. Okay, I've got a title, I've labeled my axes, I've told it I want sticks, and what I've done is I've given it these sort of inflated plotting characters for each point. So if you like to think about that as like lollipops, like if you think about this as this discrete joint distribution as like a lollipop, like a field of lollipops, that's how you do that. So this inflates the plotting character. Plotting character 19 is just like kind of a ball or a circle. Okay, so let's put this in and hope that it did everything that I wanted it to do. Sorry about that. It would be nice if... My apologies. This is how these videos become hours long. Okay. So I had these things in my editor, but I didn't actually put them in, which I do want to do. Okay, so now R knows what I'm talking about when I refer to these things. Okay, so there it is. Now, perhaps my example, this starting example, perhaps it's not so great. Because to me anyway, it's not so clear whether these are correlated or not, or whether I expect them to have a positive covariance. So this example is kind of a mystery, which is good in a way because a lot of the time it won't be entirely clear when you're talking about random variables whether they're positively correlated or not. At the end of this video, I'll show the real hard, concrete examples, obvious examples of perfect positive, perfect negative, and zero correlation random variables. But for now, we can puzzle on what we think is going on here. Does knowing the value of x tell you anything about the value of y? Well, I certainly see that as x's are increasing, there seems to be a tendency for y's to be decreasing. Like this field of lollipops does kind of seem to be extending out along maybe like a diagonal like this, but hey, but then you've got two different values, two different elements of the sample space where x is 1 with different y's, and those have kind of high probability. So it's not entirely clear to me what the case is. Okay, very good. John speaking. Courtesy call. Okay. So sorry in advance that this looks kind of like a complete mess, but I mean maybe I'm revealing the best of myself here, that I'm not entirely organized. But anyway, so let's go through and do the actual hand computation for the covariance and correlation of these random variables. So we know our formula for covariance, and we know that by simply doing the multiplication within the brackets, we can get to this more handy computational form. Okay, so what I want to do is just take each piece of this and solve for what it is. Okay, so expected value of x and y. We're allowed to do this, and okay, we're allowed to do this. We're allowed to solve this expression by saying that it's the sum over the sample space of xy times the probability of x and y. If you don't believe me, you should, because in the end, the simulation we're going to do is actually going to demonstrate that this is likely true. But anyhow, we're just going to go with it for now. So what does this mean? This means we take each xy, each point in our sample space, multiply it by the probability, and we just sum those up. So as tedious as it is, you can just start working through it. Okay, our first point was 1, 0, so we take 1 times 0, multiply it by its probability. It goes away because there was a 0 in it. Okay, next we have 1 and 1 with 2/10 probability. We had 1 and 2. 1 times 2 is 2 with 1/10 probability, so we get 2/10. Yada, yada, yada. All the ones with the zeros cancel, and we basically just get a list of things that we need to sum. And I sum them up, and I get 19/10 or 1.9. Okay, so far so good. This piece right here, the expected value of x. Well, this is very easy to calculate from our marginal distribution of x. And actually, you could have calculated it without isolating the marginal distribution and just using that joint table, because since we're not multiplying by y doesn't matter. And basically, the summation would take care of itself. Knowing the total probability of x being a 2 would take care of itself through the summation, even without isolating it. But this makes it computationally very easy. Okay, so we go through. We've got our xp of x, our definition of expected value. We go through and we get 17/10 or 1.7 as the expected value of x. For the expected value of y, we do similar. Yeah, you must be thinking, well, why are you going down here and across here? Well, because this is where there was space. Of course, of my own creation. I have no one to blame but myself. But anyhow, you crunch through that and you get 1. Okay, so now we are in a position to state what we think the covariance of x and y is. And we do that by taking our this piece, which was 1.9, and subtracting from it 1 times 1.7, which is 1.7. And so we get an answer that we think to be true, that the covariance of x and y is 0.2. Okay, similarly for the correlation, we use the piece that we just came up with, the covariance, 0.2, and we're going to be dividing that by something, and that something is the standard deviation of x, which we know is the square root of the variance of x, which we know is the expected value of x squared minus the expected value of x squared. We just got the expected value of x, we square it. To get the expected value of x squared, you take each x, square it, multiply it times its probability, sum up. Okay, so we get these two numbers here. We're going to subtract. We're going to take the square root. We're going to do the same procedure for y. We end up getting 1. We multiply them together. So to get our correlation, we take 0.2, divide by 0.71, and we get 0.256 as our correlation. Now, intuitively, this is pretty good, because we had talked about being, or I had given my opinion that it wasn't really so clear to me whether and how these random variables were correlated, but I did sort of suggest that, if anything, I thought that there might be some kind of positive correlation between them, but not super obvious. And so, I mean, that corresponds to 0.2256 pretty nicely, I think. Okay. Now, the next thing that we want to do is see if these results... Oh, okay. So before we simulate, I just want to show that you can take substantial shortcuts of doing this stuff that I just did by using R to create some functions. So what I've done is I've taken the liberty of creating functions to compute the expected value, variance, standard deviation, covariance, and correlation of discrete random variables. So just to talk through the code briefly to tell you what it's all about, I've called this expected value of a discrete random variable. It's going to be a function that's going to take a sample space and the probabilities, and as we know, the expected value is just the dot product of the sample space with the associated probabilities. Okay, so that function is good. Variance, we do a very similar thing. We use our computational formula for variance, expected value of x squared minus expected value of x, and you can see exactly what we did here, of taking our inputted x values, squaring each element of the vector to create that vector of x squareds, and we form a dot product between that and the probabilities. And then we call on this function that we've already made to get that expected value of x and square it. Okay? Standard deviation is simply the square root of our variance function. Covariance, what I did is I created a new vector that consists of x multiplied times y, exactly what I did in the computation. Okay, and over here I've used my expected value formula to get the expected value of x, the expected value of y. This actually is an example of what I was talking about a moment ago when I said you don't need the marginals per se, because your expected value operator will perform the sum for you just at like a slightly different point. So this all checks out, so I get a nice function to get the covariance. And then the correlation, of course, was just the covariance divided by the standard deviations of the random variables. So, do the results of our computations agree? Oh, sorry, that's moving on to my next point. Let me just backtrack a second and ask, do the results of these functions agree nicely with what I computed by hand? So let's go ahead. One shot drop all these guys into R. Yay, no error messages. Okay, so what do I want to ask for? Okay, if I just ask for correlation, as you can see in my covariance, I said to print covariance. So anytime covariance gets called, it's going to print. So if I just call correlation, which calls covariance, it should print everything. So let's go ahead and ask for correlation of discrete random variables, where what I'm going to use are my x values, y values, and the joint probs. Okay, and I get 0.2 for the covariance and 0.256 for the correlation, which is exactly what I got when I did it out by hand. So I have good confidence now that these functions at least work. Next, for the super fun part, which is to actually do a simulation. Okay, so do the results of our computations agree with the long-term behavior of the sample covariance and correlation given this scenario that I've outlined of drawing these slips of paper? Look at it, record what you got for x and y, put the piece of paper back into the box, shake it up again, draw another piece of paper, record what you get. Suppose I did that 1,000,000 times. Would this long-term sample behavior look like the theoretical result that I just got? Okay, so let me talk us through the code here. Okay, experiment matrix is going to basically house the results of all of those samples that I'm taking. That unthinkably tedious process of actually doing this thing 1,000,000 times, which I mean could take you probably the better part of your life. I'm just sort of making that up. But anyway, so the sample space for our experiment, I've basically created a matrix, and what it's going to be doing, it's going to have 8 rows corresponding to our 8 points in the sample space that have any probability associated with them. And I'm going to fill up the matrix by row. And there's going to be 8 rows. So I've got these 16 values, and what's going to happen is the first row of the matrix is going to be these 2 values, and it's going to go to the next row, 1, 1, 1, 2, 2, 0. So basically I'm creating a an 8 row by 2 column matrix where grabbing a given row is going to be like picking a slip of paper. Okay, so this is what I'm sampling from, and I've called this dummy row sampler. And the idea is, maybe there's undoubtedly a better way to do this, but basically I want to sample from this matrix, and I don't really know how to do that. But I do know how to sample from the numbers 1 to 8, which can correspond to the indexes of the rows of this matrix. So what I'm going to do is I'm going to get a list of 1,000,000 numbers, sampling from 1 through 8, with the probabilities associated with drawing this slip of paper, this slip of paper, this slip of paper. So I've got the 8 probabilities that correspond to these 8 rows of the matrix. Okay, so I'm all set up here. Now I have to just get R to do what I want it to do, and to do that you use a for loop. Okay, so for I in 1 to 1,000,000, and I'm doing 1,000,000 because I said I'm going to do a million of these samples. There's like 1,000,000. There's 1,000,000 empty rows in my experiment. Okay, well they're not empty. I should maybe mention that when I filled up the matrix in the first place, I mean, I could have done a replicating sequence of zeros, 2,000,000 elements long, but this is just a very handy way to do it. So if I was to print the matrix right now, it would look like 1, 2, 3, 4, 5, 6, 7, ... 199, 999,999, 1 mil. Like it would be just the numbers, integers loaded into the matrix. But this is just a placeholder for what's to come. So anyhow, what do I want in each row of this matrix? Well, what I want to do is I want to look at my ith number in my dummy row sampler. And suppose that the number for the first element of that vector was a 1. What I would want to do is I would want to go to my sample space, first row, and I'd want to grab these two guys. And then what I'm going to do is I'm going to put them into the first row of the simulation matrix. Okay, so if that needs some thought to ponder, I don't think I came up with that instantly. Putting this an index of something inside of something else. I mean, if you haven't thought through that ever before, it actually really helps to like just draw a diagram of what's going where. Okay. So once I've done that, what I want to do is I want to ask for the sample covariance, and these aren't my functions, note. These are R's built-in functions for sample covariance and correlation. I want to get the covariance between the first column of the matrix, so the matrix at blank 1, row, column, all rows, first column, and I want to pit that against what's in my output matrix in the second column. So that's all very straightforward. Okay, so let's see what happens, shall we? Okay, so we'll make sure that R likes what I'm putting in. R seems to be dragging its feet a little bit. But anyway, I have every confidence that that will go through without a bug. And let's see then what happens when, okay, and it did. And then what happens when I ask for the covariance and correlation? Okay, and I get something very close to 0.2. And I get something very close to 0.245. And those are the values that I'm after. 0.2 and 0.256. Is there cause for concern there? 0.256? Why don't I do it again? Sorry if this is really tedious, but we don't want to leave any, well, this can't shore up any uncertainty, but it can definitely help give us confidence that our samples are agreeing with the theory. 0.2 to 0.254. Okay, I mean that's good enough for me. Because there is going to be some small amount of variation there. I'm hoping everybody sort of buys what I'm saying. Okay. And lastly, okay, so to firm up our understanding of what our covariance and correlation represent, and to show that the code that we've just bothered to create, or that I created beforehand, actually has a high amount of utility and allows you to, with great speed, do those calculations that would actually take quite a while by hand, not to mention the simulations that would be impossible to do by hand in this lifetime. I'm going to show 3 more examples of jointly distributed discrete random variables and see if their behavior agrees with our intuition. So for our first example, we're just going to have 2 slips of paper in the pot. One with 0, 0 on it that has a 50% chance of being drawn, and one with 1 and 1 on it, which will also have a 50%. So based on what we know about correlation, this would be, you would have to hope that these would have a perfect positive correlation. So let's see if that's the case. Okay, so I've given it our values and the joint probabilities. So 0, 0 gets a 0.5, 1, 1 gets a 0.5. And what I want to do is just get a look at this thing. We recycle the code that we've already used, and we take a peek. Okay, so these, we see 0.5 probability of 0, 0, 0.5 probability of 1, 1, and then these guys are just sort of sitting on the plane. They have no probability associated with them. I mean, I had a choice whether or not to include them in the space at all, and I just, you know, sort of made that call to include them. Okay, let's look at the correlations and covariance. Okay, so we see indeed a perfect positive correlation of 1 in this, for this, theoretically for this setup, and also a positive covariance of 0.25. And now we simulate. Okay, and note that there are things that I had to change in the simulation to make it correspond to this situation. Maybe for future videos, I'll pare down the number of simulations that this doesn't take so long. But again, we see correlation of 1, covariance of something very close to a quarter. Okay, what about the example where we... Okay, so for our 0 correlation example, basically what I've said is let's make 4 slips of paper, 0, 0, 0, 1, 1, 0, and 1, 1, and have them be equiprobable. So let's take a look at that distribution and see if we think there's any reason to believe that the random variables are correlated. And what do we see? We see something that almost looks like the legs of a table, okay? And so you'd assume, like the intuition, does knowing something about x tell you anything about the value of y? Well, no, because if we know that we've got a 0, there's an equal chance, you know, that we had a 0 or a 1 in y. Okay. Sorry if everyone's getting very, very bored with this. So we'll do our theoretical values, and we'll do our experiment, simulation rather. Okay, so here we get 0 covariance, 0 correlation predicted by theory, and for our experimental values, we get these things which are, for all intents and purposes, 0. This is like 0.00003, and this is like 0.0000008, or something like that. Okay, so we're content with that. And lastly, we want to look at an example where we expect to see a perfect negative correlation. Okay, so here where x is 0, y is 1, and there's a 50% chance of that occurring. And where x is 1, y is 0. So in terms of the kind of line that we see here, it has a negative slope. If you can imagine this is on a blackboard and you've drawn your x and y axes typically. Well, I mean, they are drawn typically. You just have to imagine that you're flat here. Okay, and from our simulation, okay, so now our sample covariance was a negative 0.25, and our sample correlation was negative 1. You'd imagine that since this was a simulation, way off into the distance. Oh, sorry, this is not a simulation. These are our theoretical values. And for our actual sample measures, calculating covariance, we get something that's indistinguishable from minus 0.25. And our sample correlation came in at a perfect -1, but you'd imagine somewhere out here in some distant decimal place, there was some aberration from that. But this is what I wanted to show, and hopefully this has met my aims that I mentioned at the beginning of the video of hopefully getting some idea of how to visualize these discrete distributions of two random variables, these jointly distributed discrete random variables. Some idea how to visualize it, some idea how to think about what the numerical value you get for covariance, and especially for correlation. Trapping the value between -1 and 1 makes it so that you don't really have to be thinking about how extreme the values in x and y are themselves. Like, for instance, if I had instead of 0, 1, 2, 3 as values, if I had like 0, 200, 300, 400, you would get this sort of massively inflated covariance, and yet the correlations would still be what we saw. Okay, so I hope that also I gave you confidence in being able to, if you had to, do these computations by hand, as well as how you could take shortcuts using R by building functions. And then lastly, I'm hoping that by walking you through that simulation, we got some confidence not only in how to build such simulations, but in how we can confirm our computational results by using a simulation where we're doing a very large number of draws in our sample. Okay, thank you very much. Have a good day.